Greetings, Parker trigonometry students. So I threw together a quick video for you explaining the POW, so you can use it as a little refresher for your work that you're doing, or if you're unable to be in class due to illness, you can use this as a jumping off point for the POW. All right, so the situation is we have these two students, Allison and Bert, A and B. That's not a coincidence. And they start at this starting point. And at the starting point, they tie a bungee cord around each of their ankles, represented by the purple line in this demonstration. So they start at a distance of 20 feet to the east and 30 feet south of the corner of this building. Allison starts walking at 5 feet per second to the north, and Bert starts walking at 2 feet per second to the west. So that means Allison's going to cover a bigger distance in the same amount of time as Bert. So they're going to start walking. Let me move Bert back here. And the POW wants us to figure out a couple things. So the first thing it wants us to figure out is how long it takes and how far each student has walked relative to the starting point in order for this purple line, this bungee cord, to be taut but not stretched. So that means, looking back at the problem, that this length will be 7.5 feet, because that's how long the bungee cord is without it starting to stretch. Just when it gets perfectly level to the ground, not stretching yet though. So you figure that out. You want to figure out how long this is, how long that is, and right triangles. All right. Now the next thing it wants us to figure out is how long it takes and where each student is when that bungee cord hits the corner of that building. So they walk, they walk, they walk, and you can see the bungee cord gets closer and closer to that building. Eventually it's going to hit that corner right there. So the POW asks us to figure out how long Allison walked, how far both of them walked, the total time it took to get to this length in order to have the bungee cord hit the corner of that building. And though it doesn't ask, it's probably a good idea to figure out how long the bungee cord is at this point. So that's two things it wants us to know so far. So the 7.5 feet, like when it's first stretched out to that length. All the information pertaining to this situation where the bungee cord hits the corner of that building. So a hint for this one, think similar triangles. Similar triangles meaning that they are alike. We see one really big triangle right here. And we see another smaller, but still fairly large triangle right here. Are these guys similar? Why or why not? What makes them similar? Might be something you want to include in your write-up of the POW. All right, and the last thing it wants us to figure out is how far has each student gone whenever that bungee cord gets fully stretched. So it's not going to make a nice right triangle. Well, not one right triangle. It's going to make several right triangles. Something like this. It's definitely not drawn to scale. That's going to look something like this, where there's going to be a bend in this bungee cord. See, this is all one long bungee cord right here, right there. Hits the corner of the building and kind of bends outward a little bit. So not drawn to scale, but this will give you a pretty good idea of what needs to be done. So it wants us to figure out how long it takes to reach this point, how far each student has walked, like how far did Allison go to get to that point, how far did Bert go to get to that point. And it also wants to figure out this angle that the bungee cord makes with the building. All well within your capabilities as trig students at Parker, and using the Pythagorean theorem and a little bit of SOHCAHTOA in order to figure out this angle right here. All right, if you have any questions, see me the next time in class or during the day, or you can send me an email at any time. Thank you and see you soon.